Okay, welcome back. In the last lecture, we described the derivation of Maxwell relation and as well as a couple of other interesting aspects of the thermodynamic function to change the variables which are of the interest to for us as an engineer. Okay, in terms of controlling the variables which we can make use of in the experiments. Okay, so now I'm going to make use of such expressions, and we can start with something we call is Clapeyron equation. So let us consider a single component. So let's consider a single component simple system. Okay, so and the situation is such that the pressure is applied. This is a massless, let's say, piston, and you have fluid, and at this pressure and temperature this fluid undergoes phase separation, leading to a vapor phase which we say G, and a liquid phase which we say F. And we know at equilibrium your Tg should be same as Tf, and pressure is F, and as well as assuming that, of course, what we are assuming here, the pressure is there is no change in the pressure in the vertical direction, we neglect that, and as well as the chemical potential which we haven't defined, but we'll make use of it here as something called mu G and mu F. Okay, now the phase transition occurs as this P and T, and we know that based on our last lecture that the variable which thermodynamic potential which has independent variables T and P is basically G. Okay, that is Gibbs free energy. So G becomes your natural thermodynamic potential, okay, for T and P. Okay, now given that this the fluid at equilibrium, you have the same variables P and T. At equilibrium your G of fluid is same as G of gas. Okay, or in other word, dG of F is same as dG of G, the vapor phase. Okay, so this is the condition for equilibrium. This has to be same at your PT for a simple component system. Okay, and we can now make use of the definition of dG, which is as F dt plus Vf dP, and this is same as minus Sg dt plus Vg dP, or we can rewrite this as Sg Sf dt is Vg. So this is at the saturation condition because these two phases, okay, are at saturation condition, and thus we can write this as dP by dt sat is Sg minus Sf Vg minus Vf, or Sfg Vfg. Okay, so this is one expression which we came up. Now instead of making use of the equality of your Gibbs free energy for this two phase system at a given T and P which are at equilibrium, we can also directly use Maxwell's relation. Okay, so I'll try to illustrate the use of Maxwell's relation. So of course we have four relations, Maxwell relations, so we will just use one of them which relates the derivative of pressure with T. Okay, but that's what we want. Now note that here for the case of your P sat is just a function of temperature, right? Okay, it doesn't depend on the volume. So the Maxwell relation tells you that this derivative, partial derivative, is related to del S by del V at T. Okay, and as I said, P is just a function of temperature and independent of variable at or during phase change. Okay, so what we can do is I can write this as simply dP instead of partial derivative. Since it's independent of V, I can write is at simply dP by dt. Okay, and use sat as a as instead of just V. Now let's look at your PT diagram here. So at a given some t, the slope here is going to be your dp by dt. So this is sat, and this is going to be constant for isothermal liquid vapor phase change process. Dp by dt sat is going to be constant. So this is a slope at this point. Of course, this is your liquid, solid, and vapor. So what we can do is, we know this slope. Now we can try to use this directly in the Maxwell relation, and then we can try to integrate this in order to get the change in the entropy, and with respect to the change in the volume. So let me just try to illustrate that. So if we integrate this Maxwell relation here, so what we can do is this left hand side is constant, so now we can integrate the right hand side, and we can clearly get Sg minus Hf. This is integration. You had ds by dv is equal to dp at sat, and then you have this vg minus vf. So this directly comes from your fact that dp by dt sat is ds by dv at constant temperature. So this is for isothermal phase change. So I can write this as simply again sfg divided by vfg. Now it's clearly both this expression, whether I made use of Maxwell relation or directly use of the Gibbs free energy equality, you got the same expression. Now let me just work on this a bit. Since P is constant, during phase change, I can use this dH as from the expression vdp is going to be simply ds, because this is going to be 0. Now I can integrate this dH to ds from fluid to, let's say, gas, and this I can get because of the fact that the temperature is constant. This will be your sfg, so which essentially means hfg is T sfg. This aspect I can make use of it here, and I can get this expression del P by del T sat as HFG, something which I can calculate, measure experimentally, and of course this divided by TVFFG. Now this can also be generalized for any phase change, just not necessarily liquid and vapor, but any phase change from 1 to 2. Could be your vapor solid, could be any phase change. So instead of using HFG, I can write this as delta H for any phase change, this divided by T, and this is delta V, corresponding change in the volume of two phases. So this expression is called basically Clapeyron equation, is in honor of the person who actually did this exercise. Now what we can do is we can make use of this Clapeyron equation and try to simplify a bit for liquid vapor and solid vapor, where we can consider that the volume of the vapor is substantially large compared to the liquid or for the solid. So let me just simplify this expression for liquid vapor and solid vapor. So let's consider Vg VL. So this would be, let's say, at low pressure. Just consider the liquid vapor now. Therefore Vfg is going to be only Vg, And for ideal gas, this is going to be simply RT by P. Okay, thus I can write del P by del T sat as HFG, and now if it is for the ideal gas, will be your T, and the V is replaced by RT by P, so that becomes RT square, and P comes in the numerator. I can rewrite in this following form. I can bring P in here, then it becomes d ln P dt, and that is going to be HFG RT square. Okay, this is sometimes also called Clausius Clapeyron equation. So what we can do is we can further make use of this expression and integrate it considering HFG constant for small range of temperature, and I can write this as ln P2 by P1 is equal to HFG by R 1 by T1 minus T2, or in general I can write ln P is minus HFG by RT plus some constant. Okay, so what does it mean? That this expression can be used to obtain the heat of vaporization by just looking at the slope of any substance. Mostly it is true for all the gases. If you plot the saturation vapor or vapor pressure in the logarithmic form as a function of 1 by T, then you can get the slope, and the slope would be HFG by R. Thus you can find out the heat of vaporization based on this particular slope. Okay, so that will be the end of this lecture. What we are going to try is make use of this exercise, particularly Maxwell relation and then other expression which we have discussed earlier. That is your cyclic rule and reciprocative relation to find out the changes in the internal energy and entropy and enthalpy. Okay, so I'll see you in the next lecture.